All right, good afternoon. We're going to get started in just about a minute. Any questions before we get started? All right, just give me a minute. Okay. All right, sorry for the delay. All right, so let's get started with today's lesson. And just like last week, we're going to have a quiz towards the end of it. But if you have any questions about studying for the quiz or anything that you reviewed for the quiz, we can definitely spend some time going over them now. Let me know. Okay. All right. I don't hear anything. So in that case, I think we can get started with our lessons. I'm going to go through two sections in the book. One is on inverse functions. The other one is on exponential functions. And that should finish before 8, and that will give us plenty of time on the quiz. All right, inverse functions. So let's see. So we talked about functions before. So a function, let's see, f of x, you can consider is some sort of machine that takes the input x and it does something to it. And then it's going to give us the output f of x or y. Right? So the inverse, so if we flip this, so if we think, okay, so there's another machine that we take the y, we put in there, or f of x, we're going to put in there. And then it's going to do something. And at the end, we're going to end up with x. So this is the inverse function of f of x. So the notation we use is f raised to the -1. So that means inverse function of f. And we're going to talk about how to find inverse functions in a minute, but let me give you the general graphs. So graphs of inverse function. So suppose we have a function f of x given. So let's see, this is f of x. And the inverse function have the graph that's perfectly symmetric to f of x with respect to the line y equals x. So if we take f of x, we flip over the dotted line y equals x, we're going to get the graph for the inverse function. So this point here on the x-axis will be on the y-axis. This point here probably going to end up with this point there. And this point, if we reflect symmetrically, so it probably end up to be somewhere in this part. And if we connect those points, and this will be the graph of inverse f of x. So that's something, this is the fact that you should remember about inverse functions. That graphs are symmetric over the line y equals x when it comes back, when the graph is compared to f of x. So that's a graph. And let's begin with the first example. Show the following functions, f of x and g of x are inverse functions, which means that we want to show that f of x is the inverse of g of x, and the g of x is also the inverse function of f of x. Now, to show that, there's two things we have to do. So well, let me give you the problem. So suppose this problem is f of x equals x plus 5 over 3. G of x is equal to 3x minus 5. So in order to show those two functions are inverse functions, what we need to do is, so we need to show that the composition of f of g of x must equal to the composition of f of x, and both of them must equal to x. So we basically have to show f of g of x equals x and g of f of x equals x. So we have to do two parts. So the first thing we're going to do is, let's find f of g of x using the given problem. So we're going to take g of x, the 3x minus 5, we're going to put into f of x to replace the x there. So that's going to be 3x minus 5, that's the x being replaced, plus 5 divided by 3. So if we simplify this, we get 3x minus 5 plus 5 minus 5 plus 5, that's a 0. So I'm going to erase this part, divided by 3. So that's, well, let me add it there. So minus 5 plus 5 become a 0, 3 divided by 3 become 1, so we end up with x. But that's not enough. We have to go the other direction too. We need to find g of f of x, and that's going to be taking the f of x, put into the g function to replace the x. So that's going to be 3 times the parentheses, x plus 5 over 3 minus 5. Again, if we simplify this, 3 and the 3 cancels, give us a 1, so we get x plus 5. And then we subtract 5, again, the positive minus become a 0, so we get x. So now we show that both compositions of functions equals x, then those two functions. So since f of g of x equals x, and g of f of x also equals x, so f and g are inverse functions. Any questions? So to be honest, I'm pretty confident that if you take an Algebra 2 class in the past, you have seen this before, but it might have been like a few years. It will come back, don't worry. Just take some practice. So that's to show two functions are inverse. Now, what if we have a function that we don't know what the inverse is, and then we need to find? So here's a few things we have to do. So the next part is to find inverse of a 1-to-1 function. Now, let me just quickly remind you what a 1-to-1 function is. So recall a 1-to-1 function. I'm going to use 1-to-1 in this way. 1-to-1 function is a function that one output has exactly one input. And if we use horizontal line test, we can tell whether the function is 1-to-1. Because, for example, if I draw a parabola quadratic function, so this is not 1-to-1 because one output corresponding to two inputs, so not 1-to-1. But if I graph something different, let's see, I'm going to graph just half of it. Let's see, this is a vertex. I'm only going to take the right half of that quadratic function. and keep it, and then we don't keep the left half. So now if we pick a y value, draw a horizontal line, it only touch the graph at one point. So yes, now it's 1-to-1. So that's a quick kind of a check to see if the function is 1-to-1. So for 1-to-1 functions, if we want to find the inverse, we're going to follow the following steps. So steps to find the inverse, which is the first one, we're going to replace f of x with y. And the second step, we're going to switch x with y. And the step 3, we're going to solve for y. And the step 4, we're going to replace y with f inverse of x to show that what we get at the end is the inverse function. Now, you probably remember the process slightly differently, but more or less at some point, you're going to need to switch x with y and solve for the new y. But those are the 4 steps to use a correct notation. For example, let's see, given that f of x equals square root of x minus 4, we're going to find its inverse. And at the end, we're going to find, oh, anyway, we're going to talk about that later. So let's find its inverse. So the first thing we're going to do, f of x is not easy to work with in a process of solving for y or solving for x. So I'm going to replace f of x with y. So y equals square root of x minus 4. That's the first step. The second step is we're literally going to take the x and this y, we're going to switch their positions. So we get x equals square root of y minus 4. So now y is actually inside the function. It's not on the outside. So we need to solve for y. To solve for y, what we're going to do is we're going to square both sides. So we're going to square x squared, then we square the right-hand side, we got y minus 4. And then don't forget, we're going to add 4 to both sides. So we got y equals x squared plus 4. Right? And then the last step is to rewrite this y using inverse function notation, because we don't want to confuse this y at the end with the y that we started at the beginning, because remember, we switched the y and x at some point. So they're not the same y. So not the same. So this y here and the y above, they're not the same. Because this y at the end is actually the x. The x here is actually the y. So we're going to rewrite this y at the end using inverse function notation. After the -1 of x equals x squared plus 4. So this function is an inverse function, which is different from the function that we were given, f of x. So that's how we find the inverse function. Any questions? All right, so the next thing we're going to do is we're going to talk about the domain and the range of inverse functions. So for 1-to-1 functions, so domain of the inverse function, f of x, is equal to the range of f of x we started with. So if we begin with f of x, then the range of f of x is actually the domain of the inverse. And then similarly, the range of the inverse function is actually equal to the domain of f of x. So that's something important to keep in mind for inverse functions. This only works for 1-to-1 functions. If it's not 1-to-1 function, we have to restrict part of the domain and then use that part to find the inverse and then talk about the domain and range from there. So for example, in this problem we were given, so we're given that square root of x minus 4. So square root of x minus 4 is square root of x shifted to the right by 4 units. So that's how we end up with square root of x minus 4. So let's see, 2, 4, 4 is here, and the square root of x looks like this. So that's the y equals square root of x minus 4 function. And the inverse of this, it says x squared plus 4. Now, if you plot x squared plus 4, you probably normally think, okay, 2, 4. So you probably think, okay, it's x squared moving up 4 units. So you probably think about a parabola, right? Normally that's the case. There's nothing wrong with that graph if we just given x squared plus 4. But the problem is that, as you can see, they're not symmetric about the line y equals x, right? Because we begin with sort of like a half of a parabola, but we end up with full parabola. That doesn't make any sense. So we have to be careful with what we graph at the end for the inverse. We only graph what is valid for the domain and the range. So this is actually the correct graph at the end. It's not the full parabola, it's only half of the parabola. Because the domain of the inverse function at the end, so the domain of f inverse of x equals x squared plus 4 is not all real numbers. It's actually equal to the range of y equals square root of x minus 4, or f of x equals square root of x minus 4. Now, what is the range of square root of x minus 4? We can look at this function, square root of x squared, square root of x minus 4. So the range is actually from 0 going to infinity, because the lowest y value is on the x-axis. So the range of f of x, which is from 0 to infinity. So the domain of the function that we draw for the inverse, that should be from 0 to infinity. Because if we look at the domain, the x value going from 0 to infinity, that's what the domain for the inverse function is, which is the same as the range for the original function going from 0 to infinity. So that's something to keep in mind when you graph inverse functions. Always think about the domain. It's not what the function will tell you, but it's not what the inverse will tell you. It's actually the original function. You'll have to look at the range. Now, what about the range of f inverse of x equals x squared plus 4? Well, normally x squared plus 4 will going from 4 to infinity. Let's check if that's true in this case. Well, that should equal to the domain of f of x equals square root of x minus 4. And if we know how to find the domain of this function, we just need to make sure that x minus 4 is greater or equal to 0, x greater than equal to 4. So the domain, so the f of x is from 4 to infinity. And the range for the inverse function should be the same, from 4 to infinity. So we don't take the entire parabola, we only take the right half just to match with the domain there. All right, any questions about the domain and the range about inverse functions? So just think about for one-to-one functions, the domain is the range of the original function, the range of the inverse function is the domain of the original function. We can always double check that with the graph. All right, so let's see. The next thing we're going to do is, let's take more examples. So this is the example, I'm going to call it example 1. And this is the example 2 of finding the inverse. So again, we're going to find the inverse of the following function. F of x equals cube root 2x minus 4. And find domain of the inverse function. All right, let's take the function. And this, well, the first thing you're going to ask yourself is this 1 to 1, right? It's a cube root function. If you remember that all cube root functions, so y equals cube root of x, they kind of look like a square root of x, but they have a negative part as well. So they kind of like a two square roots functions pieced together in the first and the third quadrant. So the domain is from all real numbers to all real numbers. The range is also all real numbers to all real numbers. It's cube root. So any number could go into the root. Okay, so let's just note that for the original function, the domain, which is from negative infinity to infinity, the range is also from negative infinity to infinity. We're not restricting any part of the function. So everywhere of the function is fine when we try to find the inverse. So now let's find the inverse. So the first step, I'm going to replace f of x with y. So we got y equals cube root 2x minus 4. And then I'm going to switch the x with y. So x equals cube root 2y minus 4. Now I'm going to cube both sides. So we get x cubed equals 2y minus 4 plus 4 on both sides divided by 2. So x cubed plus 4 equals 2y. And then we're going to have x cubed plus 4 divided by 2 equals y. And the last step is we have to replace the y with inverse function notation. F inverse of x equals x cubed plus 4 over 2. So that's the inverse function. Now, what is the domain of this inverse function? If we just look at the function itself, obviously, you know, we can tell that x could be any number. But when we find the domain of the inverse function, we have to go back to the original function, look for the range. So the range is from negative infinity to infinity for f of x. Therefore, the domain of inverse function is from negative infinity to infinity, because the original function is a 1 to 1. As you can tell, like from the graph, doesn't matter where you draw the horizontal line, it only touches the graph at one point. It's 1 to 1. Any questions about this example?
Did you say the domain and the range, both of those are negative infinity to infinity?
For this specific example, it is. But what I wrote above was a green color. Mm-hmm. So that domain and the range, they're actually for the original function, the f of x equals cube root of 2x minus 4.
Oh, okay.
Right. But we can use the range of f of x to find the domain of the inverse function.
Okay.
Because the function is 1 to 1. Good question. You're right. So if we do need to find the range of the inverse function, we can just look at the domain of the f of x, which is, again, you're right, just negative infinity to infinity. Good question. All right, so that's this example. So the next example, example 3. So again, we're going to find the inverse of f of x equals x minus 2 squared minus 3. And then we're going to find the domain of the inverse at the end, inverse function at the end. So, well, let's look at this function. First of all, is this 1 to 1? So f of x equals x minus 2 squared minus 3, that's quadratic. And if you recall that for quadratic functions, this is like a x minus h squared plus k. So the h is 2, k is negative 3, so that's the vertex. So vertex is 2, negative 3. So if we graph it, 2, negative 3 is here, that's a vertex. And a is 1, so a positive 1 opening upwards. So the parabola probably looks like this. So that's the function. Is this 1 to 1? Well, we saw it earlier, right? This is not a 1 to 1 function. So if it's not one-to-one function, we cannot find the inverse function like we did before. So what we have to do here is we have to restrict the domain. What it means is that we're only going to take part of the function to find the inverse. So the domain for quadratic functions is from negative infinity to infinity, right? But here we're not going to take the entire domain. We're only going to take one part of it. Usually we use the vertex as the dividing point. So we're going to take the right half. Let me use a different color. So we're going to use the right half to focus on. Of course, you can see, okay, why don't I take the negative? That's fine too. But just generally, when we graph quadratic functions and try to find the inverse of quadratic functions, we're going to use the right half. So that's the part we're going to work on. We're not going to even worry about the left. So we're going to restrict the domain from the vertex to the right. Remember, the vertex is 2, -3. So we're going to go from 2 to infinity. That's where we're going to look at when we find the inverse. So from here, what we're going to do is we're just going to look at the part I shaded in blue. And I'm going to find the inverse of this function. The process is the same because the blue curve here is 1-to-1 now. So we're going to switch f of x with y. So we got y equals x minus 2 squared minus 3. But keep in mind that x is only going from 2 to infinity. It's not every x value on the parabola. And then we're going to switch x with y. So x equals y minus 2 squared minus 3. And then what we're going to do is we're just going to try to solve for y. So we got y in the middle of the parentheses. So we have to add 3 to both sides. We get x plus 3 equals y minus 2 squared. And now we're going to take a square root. You probably think, okay, when I take a square root, do I take the positive or the negative, right? And it turns out that we don't have to worry about it because when we restrict the x to be from 2 to infinity, so that means x minus 2 is always going to be positive or 0 if we have x from 2 to infinity. So here, remember the x and the y was switched. So the y here is basically the x. So we don't have to worry about being negative because y minus 2 or x minus 2 is actually greater or equal to 0. So when we take a square root, we just keep the positive value. So we got y minus 2 equals square root x plus 3. So that's the benefit of choosing the right half. And then now we're going to do is we're going to add 2 to both sides. So we get square root x plus 3 plus 2 equals y. And at the very last step, replace a y with the inverse function notation. Square root x plus 3 plus 2. So that's the inverse function. And if we were to plot it, and you're going to notice that when we plot this function, it's kind of like a square root of x, but it's being shifted left 3 units. So that's plus. So this is kind of like a square root of x being shifted left 3. That's what plus 3 to the x is. And then up 2. That's the addition at the end. So if we take square root of x, we're going to shift it left 3. So 1, 2, 3. And then we're going to shift it up to 1, 2. So we kind of get this graph. So that's the graph, the inverse function. And the original function that we picked has 2, -3. So 1, 2, 1, 2, 3. And as it goes up like this, and you probably wonder, are they really symmetric about the line y equals x? It actually is. So if we draw the line correctly, as you can see, they're symmetric over this line y equals x. So it is correct. But the one thing to keep in mind, as before you jump into the process of replacing f of x with y, switch x with y, you should always think about, okay, is this function 1-to-1, right? Does it pass horizontal line test? If it does, great, then we can go through the process. If it doesn't, we have to decide which piece we're going to keep in order to find the inverse. With parabolas, we always take the part from vertex to the right side. That way, when we take a square root at the end, we don't need to worry about the negative. So let me label that. This is f of x equals x minus 2 squared minus 3, but the black shape is the inverse. All right, so now we need to find the second part, the domain of this function. So the domain of the inverse function, f inverse of x. Now we graph it, right? We remember here we graph this inverse function. We can look at the graph, try to find the domain, which is from -3 to the right. Or we can just go back to the original function, look for the range of f of x. Remember, it's a parabola opening upwards, so it has the lowest point on the vertex, which is y equals -3. So all the y values are greater equal to -3. So the domain, just like the range of the original function, the domain of the inverse function, which is going to be from -3, the lowest y value, to infinity, or in terms of domain, is from -3, the lowest x value, to infinity. So they must be the same. So that's the domain of the inverse function. Any questions on this problem? All right, let's see. So one thing about inverse function, just remember that domain of the inverse is equal to the range of the original function. The range of the inverse is equal to the domain of the original function. So they're kind of being switched, but the sort of like the underlying condition is that the function has to be 1-to-1. All right, let's take one more example. So let's see, find the inverse of f of x, which is equal to x plus 3 over x minus 2. This is the rational function. And if we were to graph it, remember the denominator will give us a vertical asymptotes. So if we set x minus 2 equals 0, the vertical asymptote coming from x minus 2 equals 0, so x equals 2. So 2 is here, we get a vertical asymptote, and it's the divergent because we have x minus 2 to the first power. So it's a divergent. The graph diverges at this vertical asymptote. And then the horizontal asymptote, which is given by the leading terms of the numerator, which is x, leading term of the denominator, again, is x, so that's going to be 1. So we have a horizontal asymptote at 1. Y equals 1. So that at the end, it's going to approach this dotted line. And then the x-intercepts is given by the numerator. So x-intercepts is given by x plus 3 equals 0, x equals -3. So it should be a straight cross, -3 here. And then we can find the y-intercept by setting x equals 0, which is y-intercept, which is going to be -3/2 by setting x equals 0. So we get -3/2 here. So now if we take all those points and the vertical asymptotes, we start graphing. The graph probably going to be something that looks like going like this, and then divergent. So on the right side of the vertical asymptote, it's going to go up, and it'll probably eventually approach this arrow here. So that's a quick sketch. And you probably wonder, does it pass vertical line? Does it pass horizontal line test? Is it 1-to-1? It is, even though I probably didn't draw it well. So the graph probably looks like this. So it is 1 to 1. That means we can just find the inverse using the normal process. So the first thing we're going to do is we're going to rewrite f of x. So we get y equals x plus 3 over x minus 2. And then we're going to switch x with y. Note that the two x's, we have to switch both of them into y. So we get x equals y plus 3 divided by y minus 2. And then we have to try to solve for y. Well, let's get rid of the denominator first. So we get x times y minus 2 equals y plus 3. Distribute the x, we get xy minus 2x equals y plus 3. We have two y's, we have to combine them. So let's move the y's to the same side. So you get xy minus y. And then we're going to move the negative 2x to the right side. So we get 2x plus 3. And now we're going to factor out a y from the left. So we got y times x minus 1 equals 2x plus 3. Divide by x minus 1 to isolate the y. So y equals 2x plus 3 divided by x minus 1. And the very last step is to rewrite the y. So we got y equals, instead of y, sorry, f inverse of x equals 2x plus 3 divided by x minus 1. So that's an inverse function. So that's quite a bit of steps in this process. So obviously, the first couple of steps are the same, right? We rewrite f of x with y, and then we switch x with y, but be careful there are two y's in this part. Then we just have to find a way to combine them. We have to get rid of the fraction first, and then we have to combine like terms by factoring. And after that, it kind of follows naturally to isolate y by dividing by whatever the factor multiplied by y. And the last step is always the same. Okay, so any questions? Okay, so now we need to find the, let's just say we want to find the domain. So what is the domain of this inverse function? Well, we could graph it, but since I already have a graph of f of x to begin with, and f of x is 1 to 1, so what we're going to do is we're just going to find the range of f of x, the original function, since I already know the graph. So if we look at the function we had up above here, so from this graph, we can actually find the range. It's everywhere except for where the horizontal asymptote is, right? So the range is going to be from negative infinity to 1. And we do not including 1 because that's a horizontal asymptote. And it's for this case, the graph does not cross the horizontal asymptote, just based on experience. And from 1 to positive infinity. So there are two parts. One is from negative infinity to 1, and from 1 to infinity. Another notation, you can just write it from negative infinity to 1 with a union. So this is u means a union of 1 to infinity. So that's sort of like the correct sets and the interval notation. That's the range of f of x. Well, what's the domain of the inverse function? It's exactly the same. Negative infinity to 1, union 1 to infinity. Any questions about this problem? All right, any questions about any of the exercises we did today, or anything about inverse functions? So if you have not find the domain and the range of inverse functions before, just remember the takeaway is that the domain of inverse equals the range of f of x, and the other way around is also true. All right, if you don't have any questions, I think I'm going to keep going and talk about exponential functions. I'll remember to give you a few minutes break after 7. Let's see. Okay. All right, so the next part, I'm going to talk about exponential functions. Again, I don't think it's completely new to anyone here. More or less, you have seen exponential functions in the past, but you probably forget some of it. Now it's a good opportunity to review. So exponential functions has the form of the general form, which is f of x equals a b to the x. That's what makes it exponential, is the x is an exponent. And the a here is the y-intercept, because if we set x equals 0, b to the 0 is 1, so we get f of x equals a. So this is the y-intercept. It's also often referred to as the initial value, because it's a value when x equals 0. And the b here is a y, it's sorry, not the y. It's the growth factor or decay factor, and the b is strictly greater than 0. So we don't talk about a negative base. So the base b has to be positive. All right. So graph-wise, let me just make a quick table. So suppose a is positive. If b is from 0 and 1, so b is positive, but suppose b is from between 0 and 1. So we get this called exponential decay graph. So this is an exponential decay if b is less than 1. And if b is, let me move this a little bit. If b is more than 1, so a is still positive, b is more than 1, so we get this exponential growth graph. No matter b is more than 1 or less than 1, a is positive or a is negative, that's always a horizontal asymptote. So there is always a horizontal asymptote. No matter what the constants are. And the horizontal asymptote is always going to be the x-axis. So y equals 0. And if a is less than 0, then the graph is just going to be reflection. So if a is negative, we just reflect over the x-axis. And we usually don't talk about those functions because they're not quite as simple as exponential decay or exponential growth, because as a reflection of those exponential functions. We don't really talk about them that much, but you should know what the graphs look like, or at least be able to create it if you memorize the graphs when a is positive. All right, any questions about exponential functions? So always remember exponential functions is a, b to the x. A is a constant, b is a constant, b is a base, a is just a coefficient. It's actually like a times b to the x. X is the exponent of b only, not a. So don't get confused there. Now let's look at some examples. Wait. settings. I need to turn this off. All right. So let's look at some examples. We're going to talk about exponential modeling. So let's suppose. So this is the first example. Suppose there are 80 unicorns introduced somewhere on an island in 2002, and by 2004 there are 180 unicorns, and suppose they grow exponentially. Suppose the population grows exponentially, grows exponentially. We want to find a function, let's just say P of t, that will give population. I don't really expect you to write down the whole problem because I personally don't enjoy writing it down. But anyway, so with population, so we want to find a function P of t that, give population of unicorn t years after 2002. So basically, so here's a question. So we begin with 80 unicorns and in 2002, and then 2 years later, there are 180 unicorns. The growth is exponential, and we want to find the function P of t that will give the population of unicorns t years after 2000, after 2000, not 2002. Otherwise, it's going to mess up with the problem. Well, it's going to mess up with the numbers, not necessarily the problem. So that's a question. So t is the number of years since year 2000. Okay, so what do we know? Well, just like a linear models, right? So if we given 2 pieces of information, we can try to come up with 2 points from the information. So from the first piece, we have the 80 unicorns in year 2002. So we can take that and write as a point with time first and the population in the second position. So that will be 2 years from year 2000. So 2 and 80, that's 1 point. So this is the time, 2 years, and this is the population. That's from the first sentence. And from the second sentence, we can do the same thing. We can write down from 2004, that's 180 unicorns. So that's the time equals 4, and the population is 180. So now we get 2 points from the given problem, right? But the question is, how do we use those 2 points to come up with an exponential function, right? So here we know it's exponential growth. So what we're going to do is we're just going to use the general formula. So recall the general formula is f of x equals ab to the x. But if we translate into this problem using correct notation, so that will be population in terms of time. So P of t equals a constant, b is constant, the base, and to the time. Instead of having x in the exponent, we're going to have time in the exponent. So P of t equals a times b to the t. And we're going to use this formula the general form. What we're going to do is I just plug in the 2 points. So we have time and a population for each point. I'm going to plug in there to replace a t, replace a p. So if we plug in the first point, well, I'm going to plug in the second point first to make it less confusing. So plug in the second point. So we get 180. Population equals A, we don't know, B, we don't know, but we know the time is 4. This is kind of like a y equals mx plus b, right? You plug in the y, plug in the x, same idea. And then now we're going to plug in the first point. So 80 equals A times B with the 2 as an exponent. So b squared. Now we get 2 equations, 2 exponential equations. How do we solve them? Well, we can use substitution or we can use elimination, probably easier. Now, the elimination in this process is actually requiring division, not really subtraction. So now we're going to take the first equation, we're going to divide it by the second equation. So what I mean by dividing is that we're going to take the left side, divide by the left side, the right side, divide by the right side. So we get 180 divided by 80 is equal to AB to the 4th power divided by AB squared. And by doing this division, we can eliminate A because that's 8 divided by 8. And we can also simplify the B terms. So we get B to the 4th divided by B squared. So that's B to the 4 minus 2. So this is B to the 4 minus 2 equals B squared. What about the left side? Well, we can also simplify that since that's 180 divided by 8. So we can drop the 0 at the end, become 18 divided by 8. And 18 divided by 8, we can both divide by 2. So that's 9 over 4. So what we end up with is, I'm going to put it on the left. So we get 9 over 4 equals B squared. That's great because now we can take a square root to solve for B. So B equals square root of 9 over 4. Square root of 9 is 3, square root of 4 is 2. Now, I'm not keeping the negative because if you remember earlier, we said for exponential functions, the base has to be positive. So you don't have to worry about square plus minus when we take a square root. Any questions until this point? Okay, so we solve for B. So now we're just going to put it back into the general formula. So we get P of T equals A. We still don't know, but we know B is 3/2 raised to the T. That's good so far. And we still need to find A. Well, we can use one of the 2 equations we had. The first one is 180 equals A times B to the 4th. Or we can use the second one, which is 80 equals A times B squared. It's up to you. Usually I take the second equation because the numbers are smaller. So let's use the second one. So we get 80 equals A times B is 3/2 squared. So if we do that, 3/2 squared is 9 over 4. So 80 equals A times 9 over 4. So multiply by 4, divide by 9. So we get A equals 80 times 4 over 9. So that's 320 over 9. So that's what A is. And take the A, put back into this general formula. So we get P of T equals 320 over 9 times 3/2 raised to the T. So this is my exponential model. Now you probably wonder, right? Like for unicorns, how could you have 320 over 9 unicorns? Well, let's not go down that rabbit hole in this case, right? Let's just assuming that's possible because we are more interested in the mathematical modeling rather than the reality. And the unicorns don't exist anyway, so it is possible to have 320 over 9 unicorns. So that's the idea to find it, because we just given 2 points, right? We just have to come up with 2 equations, like what I did over here. And then we, generally speaking, for those type of problems, we don't try to use substitution because that's not easy. It's messy too. We just take one equation, divide by the second one. Now, if you remember earlier, I plug in the second point first. So you don't have to. You can just plug in the first point first and then plug in the second point later. And when you divide, it's up to you to either take the big number, divide by the small number, or the small number, divide by the big number. Eventually, it's all the same. It doesn't really make a difference. But if you have the bigger number, divide by the small number, it's a lot easier to take square root at the end, because chances that you're going to end up with a positive exponent, then you can just take the square root or cube root or whatever roots. All right, let's see. Let me give you another small example quickly before we take a, wait a minute, 7:06, 10:15. Yeah, we good on time. Let me give you another example before we take a break. So a second example. Let's see. Let's see. Sam bought a car for, let's just say, for $30,000. And 5 years later, the car's value is, let's just say it's 15,000. 5 years later. The numbers here, they probably don't work very well, but anyway, we can make it work. I use the calculator.
I have one question.
Okay, go ahead.
Will this formula work every time, even for dollar questions like this?
That's a good point. I think I know what you're talking about. You probably think about like a compounded interest, like a depositing money, or related to that. It works in the case if we only know, like at this time we have this amount.
If we only knew 2 out of the 3 variables.
Not 2 out of the 3 variables, but more like if we have 2 points given. Like let's say, like in this year we have this amount, in this year we have this amount. We know it's exponential growth or decay. That always works. But let's say you might have a problem that's given like, oh, the interest rate is this, and this is the initial deposit. Then we're going to use a slightly different formula.
That makes sense. Thank you.
Yep. Good. So this example is like Sam bought a car for, this amount. So that's like at t equals 0, right? That's a value. And 5 years later, the value is this. So we get 2 points because we have 2 time, and then we have 2 values of the car. Okay, so let's see. Suppose the price depreciates exponentially. So price, the value of car, so car value depreciates exponentially. So find a formula. So find a function for car's value after t years since it's bought. So the time is bought. We see the time equals 0. So t equals 0. The value is what the purchase is, right? The cost is $30,000. And 5 years later, the car value is 15,000. So we can write down 2 points like we did before. So t equals 0. The value is 30,000. And the t equals 5, the value is 15,000. So here we don't have like a compounded interest or the depreciation rate. We just have this 2 points given. So we can always use this formula, the general formula. So let's say the car value after t, I'm going to use v for value. So v of t equals a times b raised to the t. Okay, so what do we know? We can either plug in both points, see what we end up with. Probably 2 equations, right? Or we could do, we can remember that earlier from the beginning, remember we said a is a y-intercept. It's also the initial value. And by just looking at the problem, we already know what the initial value for the car is, because that's the $30,000, right? That's also the y-intercept. So we can take the number, put in there directly. So we don't have to write down 2 equations. We can just plug 30,000 for A and then use the second point to write the equation. So immediately we know what A is. So we get V of T equals 30,000 times B raised to the T. So we only have one variable to look for. So now we're going to plug in the 5 and the 15,000. So put in there. So we get 15,000 equals 30,000 times 5 times b to the 5th power. And to solve for the b here, we have to divide by 30,000. So we get 15,000 divided by 30,000. So I'm going to cross all the zeros, or not all of them, the 3 zeros at the end. Then we have 15 divided by 30, so that's 1/2 on the left. So we get 1/2. And on the right side, if I divide by 30,000, so that becomes 1. So we get b to the 5th power. And how do we solve for b? Well, to solve for b, what we do is we just take 5th root. So b equals 5th root of 1/2. I don't know what that is. Or you can write as 1/2 to the 1/5 power means 5th root, but that might be confusing for some of you. So in that case, just write as 5th root of 1/2 and put in the calculator. And I don't have my calculator with me, so I'm just going to take this number as if I know what it is. So that's my b value. And I'm going to take that and then put into this formula. So we get the value of the car is equal to 30,000 times this b, which is 5th root of 1/2 to the t. Now you can rewrite as 5th root of 1/2 as 1 over 5th root of 2 to make it look better. But I'm just being a little bit lazy at this point, because problem like this, if I give it to you, you can probably just put it in the calculator, figure out what that is. All right, any questions about this problem? So that's when you find the exponential function if you have 2 points. If you already have an initial value, feel free to use that for A. If you don't have the initial value, you just have 2 points somewhere other than the starting point. Then you need to set up 2 equations, take one equation, divide by the other one, and solve for A, solve for B that way. All right, it's 7:14 and 7:15 actually, I apologize. So I'm going to give you 5 minutes, so come back at 7:20, and there's something else I want to talk about. And after that, we can take the quiz. If you have any questions about the quiz, you can bring them. Just bring them here when we come back. All right, so break, be back at 7:20.
Instructor?
Yep.
I'm sorry about before. My Wi-Fi cut out and I had to restart our router.
Oh, no problem. Do you have any questions?
No, I do not.
Okay.
Thank you.
Yeah, don't worry about it. Yeah. All right, I'll be back shortly. Let me go to the restaurant. All right, welcome back. So let's see. We're going to keep going, and I have a couple of things to talk about, and then after that, we should be able to take the quiz. So let's see. All right, so now we're going to talk about compounded interest and also just annual growth model. So we talk about the general formula, which is f of x equals ab to the x. Now, so the next part is the annual growth model, which has a formula of a of t equals p of 1 plus r to the t. And p here is kind of like the a, which is the initial value. And r here is the annual growth rate. This is called the nominal rate. And then later we're going to talk about the effective annual rate, which is different from the annual growth rate. And since we talk about annual growth, so the t is time in years. And the 1 is just a 1, and there's nothing fancy there. So that's the annual growth model. We're going to work with some examples in a minute. And note, if r, the annual rate, is positive, we get the exponential growth. And if r is negative, we get an exponential decay. Which is different from above, which says if b is less than 1, we get exponential decay. If b is more than 1, we get exponential growth. They compare to 1, the growth factor compared to 1. But here, if we just look at the growth rate, r there, if it's positive, it's growth. If it's negative, it's decay. Because if r is positive, that means 1 plus r is more than 1. If r is negative, then 1 plus r is less than 1. So there's no contradiction there. It just depends on which part we're looking at. All right, so that's that one. And then the next one is the compounded interest formula. So compounded, let's just say compound interest formula. Which is a of t equals p 1 plus r divided by n times t in the exponent. Now this is similar, so the p is the initial value. But usually compounded interest formula, the p is the initial deposit, it's how much we put in at the beginning, or initial deposit. So initial value, hold on, let me see, initial value, or the initial deposit, which is principal. Right? And n, so r is still the annual interest rate. So r is still the annual interest rate. But there's two new additions, which is the n in the denominator and this n. So n here is just the number of compounding periods. So how many times is the interest being calculated or compounded during a year? So number of compounding periods. If the problem says the interest is compounded, let's see, daily. So let's see, if it says daily, so the n will equal to how many days? 365 usually. If it's a monthly, we just have to think about how many months in a year, which is n equals 12. So n is the number of compounding periods in a year. Let me be careful there. Now, what if it says compounding annually? Means that the interest is only calculated at the end of each year. Well, if it's compounded annually, so n equals 1 because it's 1 year in, well, 1 year. In that case, the first formula, the annual growth model and the compounded interest is actually the same formula if n equals 1. So if it's compounding annually, so this is the same formula as above. The same formula. But if it's not compounding annually, then it's not the same formula because there's like an extra n in the denominator and also in the exponent. So that's this one. So the next thing I want to talk about is, let's see. Well, let me quickly check. Does everyone know what the number E is? Anyone doesn't know what E is? So let's see. So recall the number, the natural number. E, by definition, you don't have to memorize it, but it's good to kind of know what it is. There's a 1 plus 1 over n raised to the power of n. So that's what E is, with n goes to infinity. And we usually just approximate this to be 718, I think. And to be honest, every time we use it, the calculator approximates for us. And the E, just remember, it's like pi. E is like pi. It's just a number that we use it for many things in mathematics, but it's not an ordinary number. It's some unique number that developed. All right. So why do we talk about this? Well, there's something called compounded continuously model. So it's still compounded interest formula, but it's for the continuous model. So continuous growth, decay, or maybe compound interest. Model. So what this one is that instead of compounding, like instead of the interest is compounded like every second or every half a second, right? It just always compounded. So that's like for infinitely small time intervals. So the interest is being calculated. So it's continuously calculated. So the formula is a little bit different. So we have A of t equals P E raised to the RT. So there's no n here because we don't talk about how many times it's compounded. It's continuous. So R is the continuous growth rate. Now, we don't really talk about this being like an annual interest rate, but most of the time when we give in an interest rate and it's for continuous growth, we pretty much assume that the continuous growth rate is more or less the same as the annual interest rate. Pretty close. And the P here, again, is just the initial value. And the E is just E. This E is a number. So this is a number. And the T is time in years. Usually that's the case. And again, a couple of things to note here. So if the continuous growth rate R is positive, then we have exponential growth. If R is negative, we have exponential decay. All right. So any questions about those models? So here we have, I know there's just a whole bunch of formulas I'm throwing at you. So there's the annual growth model, there's a compounded interest formula, and then you have this continuous growth or continuous decay model. Now, one last thing I want to talk about before I jump into some examples is effective interest rate. Now, effective interest rate is usually happen when we have compounded interest models. So what happened with compounded interest model is that, let's say if it's compounded monthly, right? So the interest generated in the first month actually stays in the account, and during the next month, the amount of interest you created in the first month actually give you a little bit extra interest, and every month the interest you gain stay in the account, and that creates more interest. So in the end, what you end up with as the interest for the whole year is actually more than what you should get if it's just compounded once a year. So if it's compounded like more frequently, it's actually a good thing because you allow the interest to create more interest in the process. So that's why we talk about effective interest rate, which is sort of like in reality, at the end of the year, what is the overall interest rate compared to the nominal interest rate? The annual interest rate is more like the theoretical interest rate. That's how I remember it. So if we want to find the effective interest rate for compounded, for annual growth model, A of t equals P1 plus R to the t. So the effective interest rate is actually equals R, exactly the same as the annual interest rate given, because you only calculate the growth once a year. So whatever the rate is, it's the same as the effective interest rate. But for compounded interest formula, so the A of t equals P1 plus R over N to the NT. Now the effective interest rate is actually not equal to R. It's actually equal to 1 plus R divided by N raised to the N minus 1. So that's a 1 plus R over N squared, parentheses raised to the N minus 1. So that's the effective interest rate. You basically drop the principal, drop the T, take whatever is remaining, calculate that, minus 1 at the end. And for continuous growth, model, so that's the A of t equals P e to the RT. Again, we're going to drop the P, we're going to drop the T, and subtract 1. So that's going to be the effective interest rate is equal to this part, e to the R minus 1. And if we go back to the first part for the annual growth, you can think about the same thing. If we take the P and drop it, and the T drop it, we get 1 plus R, and we subtract 1 from it, 1 plus R minus 1, we get R there. So everything works. So it's always the part without the principal, without the time in years, and then minus 1. All right, I know that's a lot of formulas to throw at you. Let's take some examples. And I think the examples will go by quickly, just to practice those formulas. So let's see, suppose we deposit, let's see, $500 into a savings account that has a annual interest rate. So this is annual, has an annual interest rate of 0.3%. So that's the interest rate, 0.3%. So we're going to write a formula for the balance for each of the following cases. So write a formula for balance. Oops, wait, go away. So the first case, it says it's compounded, let's see, annually. So the interest is compounded annually. So what is the balance formula? Well, we have a deposit 500, so that's the initial value, right? We also have an interest rate, 0.3%, and it's compounded annually. So I can either use the compounded interest formula with n equals 1, or I can use the annual growth model. It doesn't matter, they give us the same. So the balance, you can use A of t or B of t, doesn't matter. That's going to equal to the initial deposit, the principal, which is going to be 500, the initial value, times 1 plus the interest rate is 0.3%. But if I put into decimal form, I have to take 0.3 divided by 100. So that's going to be 0.003. So be careful there. So 0.003 raised to the t. So that's the compounding annually model. And then the second one says, okay, what if we have it compounded monthly? Okay, if it's compounded monthly, we're going to have to use the compounded interest formula. There's no other formula that works. So the balance A of t is going to be, again, the initial value doesn't change, 500, the principal. And then 1 plus r over n, so we have to know what rate is. The rate is the annual interest rate. That's a 0.3%. So that's a 0.003 divided by n. We have to know what the n is. Compounded monthly, n equals 12. So divide by 12. You can think about, the way I look at it is always this part, the rate divided by n, that give us the rate for every month, right? So what is the rate for each month? Well, we take the annual rate divided by 12, we get the rate for every month. And then we're going to raise to how many months we have, which is the same thing as 12 times t, because t is the number of years. We always keep t as the number of years if we given the annual interest rate. So you can think about, okay, the exponent 12 times t is how many months in t years. Any questions? So let me say, you can think about this is like, this is a monthly rate. And this is the number of months. Kind of like the first formula, we have the annual rate. This is the number of years. You can think in that way. Or you can just remember the formula and try to plug in what we know. All right, how about number 3? Let's see, we want it to be, let's see, so that's monthly. If it's daily, we just change it to 12 to 365. Now, suppose 0.3% is also the continuous growth rate. And compound the interest is compounded continuously. What's the balance? So now we're looking at a continuously compounded interest model. So it's compounded continuously. We're going to have to use a different formula. It's not the compounded interest formula. We're going to have to use the continuous growth model, which is A of t equals P, the initial value, which again is 500. And then we have to use e raised to the RT as my formula. So e raised to the R is 0.003 times t. So that's a unique case. Any questions about those three examples? So if it's compound annually, just think about either the annual growth, the regular one, or you can think about compounded interest formula, but make sure n equals 1. Or if it's not compounded annually, like a monthly, daily, quarterly, weekly, we're going to have to use the compounded interest formula divided by the number of compounding periods in a year. If it's compound continuously, then we're going to have to use the continuous growth model, PE to the RT. All right, any questions about what I did? Okay, all right, let me know if you do. I'm kind of going through this. Maybe it's a little bit too fast here, but let me know. All right, so we did this. Let's see. All right, let's see. Let's take the fourth example. It's the same setup. Let's say, suppose we have still take, $500 put in there with the annual interest rate 0.3%. Suppose compound weekly. And if you recall that there are 52 weeks in a year. So what is the effective? I'm not looking for the balance. I'm looking for the effective annual interest rate. Right. Well, let me just kind of show you from the beginning. You don't have to start this way. Suppose we're looking for the balance. We know that A of t equals the initial value 500, 1 plus R 0.003 divided by the number of weeks, 52, raised to the 52t. That's the balance. But I'm not looking for the balance. I'm looking for the effective annual interest rate. So I'm going to drop the principal. I'm only going to take this part. Don't forget the exponent 52 there. So take this expression, and I'm going to subtract 1 from it. So effective rate, interest rate, is equal to 1 plus 0.003 divided by 52 raised to the 52 minus 1. So put this into the calculator. That will give me the effective interest rate. It's not going to be 0.3%. It's actually a little bit higher. But it's not going to be 0.4%. It's not that high. It's just a little bit higher than 0.3%. It's not too crazy. All right, any questions about this problem? All right, so the next problem I have, let's change the problem, not the same setup, but similar. Let's see Sam wants to, wants to end up with $5,000 in 10 years in a, let's see, in a money, oops, I can't spell money market account. But some kind of like an investment account. Let's just say investment. Account. And the investment account has a with annual interest rate of 5% compounded. Let's say compounded quarterly. So how much should he put into the account to begin with? So how much should he deposit initially? Okay, so that's a question. We don't know the initial deposit, but we know that he wants to end up with $5,000 in 10 years. And we know the account has an annual interest rate of 5% and a compounded quarterly. Right. Well, problem like this, what do? We're going to begin with, write down whatever we know, right? We know it's a compounded quarterly, so we're going to use compounded interest formula. And then we decide what we know and what we don't know. So A of T, the balance, is equal to P, the initial deposit, times 1 plus the interest rate is 5%, so that's a 0.05, divided by quarterly, so N equals 4 quarters in a year, raised to the 4T. So that will be the general formula if we know the principal, and that gives the balance. Well, we don't know the principal, and we do know the balance in 10 years, right? That's 5,000. So now we can plug in T equals 10 and the 5,000 as the balance. So plug in T equals 10 and balance equals 5,000. So that will be 5,000 equals P, we don't know, 1 plus 0.05 over 4 raised to the 4 times 10. And I don't have my calculator. A problem like this will require a calculator, so we should be able to calculate this part. And then we're going to divide that expression from 5,000 to get P. Is it okay if I leave it like this? All right, so we can solve for P from here. Any questions on this? I know you're probably all anxious about taking the quiz. I promise you, I only have one more problem to go over, and then we should be all set. You know what? Let's see. Let's stop here. I have one more problem, which is the exponential decay. I think we can leave it for tomorrow because tomorrow is just a review day. Let me leave it for tomorrow. And any questions before the quiz? All right. Let's see. No questions before the quiz. Oh, about tomorrow, I just want to say that I'm not gonna prepare any sort of like a review material, but I think it's an opportunity for you to ask questions. It'll be great if you find some questions and basically like start reviewing for the exam. Find some questions from the homework, from lecture notes, from just anything that you are not certain about. Bring them to the class tomorrow, then we can go over them. Any questions? All right.
Sorry.
Oh, go ahead.
Is it the same time that we had last time for the quiz as well?
Right, the quiz is today, right? So I'm going to start the quiz soon. I mean, normally the quiz takes about 20, 30 minutes. So if we start now, that should still give us plenty of time to complete and upload it before 8:40.
Okay, thank you.
Right. And if you have extended time, I know there's a couple of students here that, you just kind of multiply by 1.5 and and I guess 40 minutes time 1.5, 1 hour. I think that should be enough. And then you can just upload that to your work. All right. And let's see, anything else? So that's the quiz. Tomorrow is the review day. And like I said, if you miss I forgot to record last lecture, the first few minutes when I talk about the exam on Monday. Again, you don't have to come to class on Monday. When class begins 6:10, I'll make the exam available to you. So you just write down the solutions in your notebook. When you finish, you can upload them. Just make sure that it's one PDF file. Just could have many pages, but it's just one PDF file. And you just upload it there. If you have any questions, I'll be on Zoom during that time. But if you don't have any questions, you don't even have to show up. Just complete the exam during that class time and submit it afterwards. All right. Any questions? Oh, and I said pretty much everything we covered until today. And there's one example I'm going to talk about tomorrow. Anything we talked about so far could be on the exam. So yeah, so be prepared. All right. Any questions before I open the quiz? Let's see, what's my quiz? Let's see. Give me a minute. Should be ready in a minute. Let's see. All right, it should be published now. So if you go to either pages or if you go to modules, you should see quiz 2. Wait, what's quiz 2? Well, if you go to pages, you're definitely going to be able to see quiz 2, and you can open it and start working on it. Let's see if you go to modules. I don't know. Actually, you don't see quizzes in modules. Yeah, just go to pages and let me know if you cannot open the quiz. If you have it open, feel free to leave. You don't have to stick around on Zoom, just like before. Feel free to leave and work on it. If you have any questions, come back here. I'll be here. All right.
Thank you.
All right. Take care.
Thanks.
Good luck. Yep. No problem.